know this is a chair, and now I have a new image, and the question is it a chair? So what I can do is I will extract a sub-patch of this image, this one, and I will try to find it in this image. And really concretely, how can I find a sub-patch of an image in another image? We should look at how the sub-patch are represented on a computer. It's only an array of numbers, and here we can see that it's an array of pixel intensities between 0 and 255. And now I have these two arrays of pixels, and how can I compare them? And one of the most simple way to compare two arrays of values is a scalar product. So the scalar product here will take two arrays of values. Here I have 1, 2, 3, and the second array is 3, 2, 1. And I multiply component by component, so I will obtain 3, 4, 3. And then I sum this array, and I will obtain a score of 10. The scalar product have a geometric interpretation. So here I have my scalar product between two arrays, x and y. And if I divide it by the length of, I need a norm of the length of my vector. If I divide the scalar product by the product of the norm of the two vectors, and I take the arc cosinus, I obtain the angle between the two vectors. And in fact, if the angle is 0, it means that the two images are perfectly aligned, except for a scaling factor. So all the pixels would be the same, but maybe I can scale the intensity of all the pixels with a single scatter. But it means that the two images are very close to each other. If the angle is pi over 2, it means that the dot product is 0, and there is not a lot of similarity between the two. It's also called the cosine similarity. It's only for the intuition. We don't use the full geometric interpretation of scalar product in deep learning. We just use scalar product as an elementary operation. But keep in mind that we are trying to see if two images are similar or not by computing their scalar product. So let's try. I have my full image that I want to predict if it's a chair or not, and I have my sub-patch here. And I can see that the value of a normalized version of scalar product, if it's 0, it means that the patch is not there. If it's 1, it's perfectly there. And here at this location, no, the pattern is not here. It's 0.1, it's not. Here we can say that maybe it's here. There's some alignment between the pixel at the bottom, but because the leg in my sub-patch is a little bit not straight, I don't have full alignment. It's only 0.5. And here the alignment is better, so the score is higher. And I will say probably the pattern is here. But as you can see, this sub-patch is a leg of another chair. And only by chance, I found this pattern on the back of the second chair. And you will say, this is not the same semantic. Even if my pattern recognition say that the pattern is there, this is a leg, and it has been found on the back of this chair. So the semantic doesn't align. But since we are only comparing numerical value, there's no notion of semantic. It's only comparing pixels together. So if I want to scale it to try to solve this problem, probably I should use a lot of patterns to see if all the sub-part of a chair is present in this image. So I will use a lot of patterns that I will iterate over the image, retrieve some score. I will have a vector of scores, and I can give it to a simple machine learning model. And also the score, we can see it as new features representing the data. So I will have a new vector with the score associated to each pattern if they have been found in the image or not. And in fact, all these scores is a new representation of my image. It describes the image in terms of the patterns that I have used. So one question is, why did I use only a small patch like this to compare it to try to find this pattern in my image. Why was it important to use a small pattern here? Because if I use the whole chair, the probability that it will perfectly match is very low. All models of chairs are unique, and if I use the whole complexity of the pattern and I try to look at it in my image, I will not have a high score at all, because only if I change the orientation of the chair, the pattern will not match at all. And so using subparts that are simple, that are very small patterns, and trying to look at it in my image, the probability to find the small parts is higher than using very complex pattern from the beginning. It correlates more easily. So this is one of the most important idea in deep learning. This is the compositionality principle. So the whole complexity of a chair, in fact, it's made only from its part, only from tiny parts that we combine together to create a complexity, an object that is complex. And we can also compare it to Lego blocks. If I just take one Lego block and I try to find it in this image, I can say this Lego block is here, 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 and here. If I use a more complex block and I try to find it, then it will be harder to find. And if I use the whole town here and I try to find it elsewhere, the probability that I will find such complexity elsewhere from the beginning by using the whole complexity as a pattern will not work. And so we have this notion of when we are close to the data, we want to use very simple pattern, and then we will have a new representation, and we'll try to extract patterns that are a little bit more abstract from this second layer, and then we obtain a new representation. Again, we try to extract patterns from this representation, and we continue like this until we are at the end of the model to do our prediction. And this is the idea of deep learning here. Instead of trying to handcraft our own feature like I did with this chair, we will let the model to extract the feature itself, but we will give the capacity to the model to extract a simple feature at the beginning, and then build features that are more and more complex until the end of until here, where we will predict a complex object like a cat, a chair, or something else. And so we can ask ourselves, what are good representation here? If I have this deep learning model, and I have my feature extractor that works at different level of complexity, here I have all the image with a lot of information, then I will extract features that become more and more abstract. And here at the end, because I'm still using a very simple classifier, like a linear regression, I want all the images of cat to be on this side, and all the images of dog on this side, and only a linear classifier will be able to separate the two. So it's like using this, this hierarchy of feature, every layer of representation will help the next layer to produce representation that are simpler and simpler for the task. And at the end, the representation are so abstract and so well organized in the space that only a linear classifier will be able to distinguish two different classes that are really hard to describe in terms of a program.